Hey guys, are there any questions before we get started? So again, if there are any questions before we get started, we have a few minutes. Okay, then let's get let's get started. So you should all have gotten an email about the homework being postponed and about the dates for the oral exams. And lots of you have already written back about the oral exams. There is an announcement on Canvas that lists all the slots, and it lists who has signed up for what. So go check there and make sure I didn't make a mistake when I put you in. If I made a mistake or if I overlooked your email, just contact me again and I'll get it updated. Okay, so with that being said, let's push on, continuing on the martingales that that we had talked about last time. Right. So last time, we introduced martingales. Right. So what you have is you have either an infinite sequence or you have a finite sequence for some natural number. So you have a collection, and then you say that this is a martingale. Well, one is that it's adapted. So remember that means that Mn is Fn measurable. It's integrable. So that means I'm going to take the expectation of the absolute value of finite. And it has this property that if I try to estimate the future value, so we're thinking about these indices up here as time, it has the property that if I try to estimate what the process is at a later time, given where I am today, I'm just going to get the current value. So I have a sequence or a collection of random variables to satisfy properties 1, 2, and 3. Well, then I'll call such a sequence of random variables for a martingale. sometimes you will see, sometimes you will see 3 iterated. So what that means is that right here we have mn plus 1 and you have n. Sometimes you will see something like e of m n plus, say, 2 given fn. And we can work out what this is. But because we can use conditional expectation, we can put in an additional conditional expectation. We know that if I have 2 conditional expectations next to each other, the smallest one wins. So here I can write fn plus 1 and then condition on fn. This is iterated expectations. Iterated conditional expectations. And so then we can use the property that it's a martingale. So the inner conditional expectation, I can find using the property up here. This is going to be mn plus 1. So then I'll have the conditional expectation of mn plus 1 given fn, because that was the inner conditional expectation versus mn plus 1. So what it allowed you to do is to swap out n plus 2 for n plus 1, and then you'll get mn. So in particular, so you can keep doing this, so you can put anything you want here. In particular, if you were to compute the expectation of mn with no conditioning, in particular, if you were to compute the expectation of mn, you could see, for example, if I took mn plus 2 here, I would then take the expectation of the left-hand side. This would be right. If I took the expectation of the left-hand side, the expectation of the conditional expectation is just the unconditional one. And you'll see mn plus 2, this is going to be exactly the expectation of mn. Right, I can replace the inner conditional expectation by mn. So I'll get that the expectation at time n plus 2 is the same thing as the expectation at time n. So the process mn has constant expectation in the sense that no matter what index I put in, I'll always get the same as just the initial one. Right, so martingales have constant expectation over time. Okay, does that make sense to you guys?
Yes, can you give intuition as to what that serves for?
The constant expectation property?
Yes, please.
Yeah, so this is not in general a property that one would expect to have, but for example, if we look at it, if we bring this here is general, right? This is not specific to math finance. If we bring this material here into a quant finance setting, so we're going to use, we have talked a little bit about the multi-period binomial model. And so the multi-period binomial model, just to remind you, right, I have these Bernoullis, These were IID coin flips. So we had, the model was it could be U or D with a probability P with a probability 1 minus P. And so I have my stock price. My stock price, I would start it out somewhere positive. And then I would get the next stock price simply by taking the previous one and then times one of these Bernoullis. And of course I can write out, this is the same thing as Sn minus 1. Then I'll have psi n plus 1. And I can keep doing this and I'll end up with S0, psi 1, psi 2, product all the way up to psi n plus 1. And so I have such a thing, and I could ask, is this a martingale? Is Sn is Sn the sequence? Is this a martingale? But so one way to disprove that it's a martingale, I could see if it has constant expectation, right? So if yes, well then the expectation of Sn should be, well, S0, right? That's a constant. This is a positive. This is a constant. Right, so if the initial value is a constant, I don't have to take the expectation. And so if yes, then we have to have this for all n. And so do we have that? So let's see if we have such a property, right? So if it is a martingale, well then one of the implications from being a martingale is that you have constant expectation over time. Well, so then let's try to work out what is the expectation. So the expectation of Sn, we'll use the formula, say. This here will be S0 times the expectation of all these coin flips. And these were given to be independent. So this here is because we have independent. We have independence. So here we have S0, then we have an expectation, psi 1, expectation of psi 2 times the expectation of psi n. But we also know the IIDs, right? So the identically distributed, the independent and identically distributed. So I know what this stuff is. This is S0, and then you just take one of them to the power n. And this here is because you are identically distributed. So if this is a martingale, that means that this expectation here should be 1. We don't have that. But we don't have that this is equal to 1. We don't have that. However, we don't necessarily have that the expectation of these psi 1s is equal to 1, right? On the other hand, we know exactly what it is. It is P times U plus 1 minus P times D. We didn't make no assumption that this is 1. So that means, so no, the stock price is not a martingale. Did that shed some light on the property of having constant expectation?
Yes, very much. Thank you.
So we actually did something last time. However, to make it even more confusing, we did have a martingale property last time. We did see that this S tilde, which was S divided by the money market account, 1 plus R to the power N. We did see that this was a P tilde martingale. And how did we see that? Well, remember, to check the martingale property, the martingale property is not given by this property. This here is an implication of being a martingale. If you want to prove that something is a martingale, you have to check properties 1, 2, and 3. So if you want to prove that this is a martingale, well, we have to do more work. So we will have to compute the expectation under that measure we're looking at. And then you have to have S tilde n plus 1 given Fn and work out what this is. And so what we'll be getting here is, there's a constant in here, he can travel outside. And then you have 1 plus R to the power n plus 1, conditional expectation in here. And then you have Sn plus 1 given Fn. And so what we would get would be 1 plus R n plus 1. And then this guy, so we'll have to use the definition. This here would be Sn psi n plus 1 given Fn. Right, that was the definition of the stock price in the multi-period binomial model. We would then do 1 plus R n plus 1. And then you pull out, this thing here is measurable. So you can go outside. And then what's left here is going to be independent of Fn. So you just get the unconditional expectation. So here we use two properties. For this one here we use that Sn is Fn measurable. And we use that psi n plus 1 is going to be independent of Fn. And so we use these two properties. And then we will work out what is that inner expectation. Well, it's a Bernoulli. It's a concept. So we'll have that this is P tilde times U plus 1 minus P tilde times D. And so when you plug in what P tilde is into this formula, you end up with this thing being, this here is going to be 1 plus R. You divide out what the 1 plus R is here, and you're going to get that this is Sn divided by 1 plus R to the nth. And so this is exactly S tilde n. So we did see that even though S is not a P martingale, the discounted stock price has a martingale property, but under these different probabilities. So this is like a prototype. This is for us in quant finance, this is a very important martingale. This is something we will use quite a bit. And it doesn't matter if it's in continuous time or if it's in discrete time, you'll have a martingale property when you discount the stock by the bank account.
Why is it called P tilde martingale?
Because you're computing expectations under the tilde measure. Right?
Oh, okay.
Okay. Gotcha. This is the expectation under the tilde measure. This here would not work had we written this under, had there been no tilde here, we'd have to put P here. But you don't know, if I put P's here, there's no formula for P. There's a formula for P tilde. Like this equality sign here, this equality sign uses that P tilde is defined as, what was it? It's 1 plus R minus D divided by U minus D. Actually, take that formula and plug it in here, and it cancels out 1 divided by 1 plus R here. Are we good so far? What we're going to be doing now is we're going to push this. So now we have a property, we have a martingale property of the discounted stock price. This martingale property leads to other things being martingales. So that's what's going to come next. So the wealth process, inherits this martingale property. This is not completely obvious to see, so we're going to take this slowly and try to argue why that's the case. So first, the wealth process is the wealth, so I should say here the discounted, everything has to be discounted. The discounted wealth process inherits this martingale property. So first we look at the wealth, and the wealth is Xn, right, so this is the definition. You look at the number of money market account units you have times the money market account plus the number of shares you have times the shares price. And that's your wealth. And as we talked about, there is a self-financing condition. So this here is called the self-financing condition. The self-financing condition. The self-financing condition. And the self-financing condition says that if I'm interested in the wealth at a given time, so this is a definition, this one here is a property. It says that I cannot generate money out of rebalancing. So what does that mean? It means that if I look at the positions that I had before trading, right, so I had these positions here at time n minus 1 before trading. If I rebalance, so I buy and sell some bank units and I buy and sell some stock units. So I rebalance, I go from this holding in the bank and this holding in the stock to these new ones. I cannot generate money. I will have that the value I have after rebalancing is the same as what I had before rebalancing. So this is the self-financing condition. And we'll always be using wealth processes that satisfy the self-financing condition. We will sometimes have to expand this. We can allow for consumption and we can allow for income. So we can do more than just buying and sell the bank and the stock. We could, for example, consume. We could, for example, receive dividends on the stock, and we could, for example, receive income from labor. I don't think we're going to be doing this in this course, but in principle, this can be adjusted to that. So what we'll be hunting for is a martingale property of this kind of wealth process. So to get there, I first need the wealth dynamics. And the wealth dynamics, this is simply just a change. How does this stochastic process, how does it change over time? So the change in the, this here is defined to be xn minus 1. Right, just a change. There's a question. Is the self-financing part of no arbitrage? No. Investors are restricted to only use self-financing strategies. And then the question is, can you find arbitrage strategies among the self-financing strategies? So we will always be using self-financing strategies, and then the question is, will I find arbitrage opportunities within within those. And hopefully the answer to that question is no. Yeah. So to have an arbitrage, it means that you're using a self-financing strategy. But I can talk about self-financing strategies without talking about arbitrage. We're not talking about arbitrage at this point here. Okay, so we're looking at this change in X, and I want to find a formula for it. So we start out. I simply just use the self-financing condition. That's going to be my first xn, delta n minus 1, 0, Sn 0, plus delta n minus 1, Sn. Right, and so for the second one, I'll just use the definition, delta n minus 1, 0, Sn minus 1, 0, plus delta n minus 1, Sn. And then what we do is we combine terms. You'll have Sn0, and I'll have minus this guy. And then I'll have the same thing for the stock holdings. Okay, so then I'm going to be using, how does this look like in the bank account? Well, the bank account says that Sn at a later time, I'll get as the previous one times 1 plus R. So I'll see that this difference here is delta n minus 1 is 0. And then I'll get Sn minus 1, 0 times R. And I'll just keep the other one. Okay, so then I'll have the first term here. I'm trying to get rid of this delta naught here. So I'll use the connection, the same formula that took me down here from this term. These two terms are equal. So if I'm looking at, and I'll recover this term here, and that's the one I have here. So this will be xn minus 1 minus this term over here. And so this term here is going to be xn minus 1 minus delta n minus 1 Sn minus 1. And so I can combine everything. I'll have this as R xn minus 1. And then I'll have my delta n minus 1 outside. Inside, I'll have Sn minus 1 plus R Sn minus 1. And I have my R here, minus, this is going to give me the minus R Sn minus 1 over here. I have delta n minus 1 is outside. So that's kind of this is the first calculation towards proving this, this statement up there. So my discounted wealth process, this is defined, as x n tilde. It's just the undiscounted one, and then you divide by the money market account, 1 plus R to the nth. So this is very much the same as when you did Sn discounted. This was Sn divided by 1 plus R to the n, right? These here are definitions. And now what I want to do is I want to figure out what are then we figured out what the wealth dynamics were. So now what are the discounted wealth dynamics? So we do the same calculation as the one we had here, but we do it for this X tilde. So the discounted wealth dynamics this here this is part of a theorem that is known as the Numerian invariance theorem. We're doing a special case of a much more general theorem known as the Numerian invariance theorem. So let's look at this kind of wealth dynamics and see what we can get out from it. I'll start out checking. I'm going to be using what we just did, spent so much time doing it, so I want to start by doing that. So we will first have that xn is equal to, okay, so I have my xn here, and I have this mess down here. I'll just move this xn minus 1 here over on the other side, so I'll get 1 plus r here. And then I'll get xn minus 1. And then I'll have the other term, this part here. Okay, so I just used this long calculation we did here. The only thing I did was I took this term here, moved it over on the other side. Instead of r, I'll get 1 plus r. So this is what I have here. The second term is exactly the same. Just copy it down here. So if I have that, I can divide by 1 plus r on both sides. And if I do that, I'll get xn minus 1 plus delta n minus 1. I'll get Sn divided by 1 plus r minus Sn minus 1. And I'm going to use this calculation here when it comes to figuring out what the discounted wealth dynamics are. I need to calculate delta xn tilde. But just as before, this is defined to be xn tilde minus xn minus 1 tilde. Okay, I'll use the definition. I'll use the definition. This here is xn divided by 1 plus r to the power n minus, and then I'll have xn minus 1 divided by 1 plus r to the n minus 1. And of course, I can collect terms here. I can pull a factor outside. This is 1 over 1 plus r to the n minus 1. And then what I'll have inside would be xn divided by 1 plus r minus xn minus 1. This is why we did this calculation up here. This is why we did this calculation up here, because that difference is exactly what I have here. So I'll get something, I'll be able to get this difference here by moving this term here to the other side. I'll just have what will be delta n minus 1 times Sn divided by 1 plus r minus Sn minus 1. Okay, so I'm almost there now. This is going to be delta n minus 1 times, and I move this factor back inside, Sn 1 plus r to the nth minus Sn minus 1 divided by 1 plus r to the n minus 1. And I'm good because this is exactly delta n minus 1 Sn tilde minus Sn tilde minus 1. This is exactly delta n minus 1 delta Sn tilde. So this is the wealth dynamics of the discounted stock price. Oh, the discounted wealth. This is the dynamics of the discounted wealth process. And you can see it's quite similar. It's not very far away from what you had over here. And indeed, you can see that when I am in a discounted market, this amounts to R simply just being 0. Because if I take R to be 0 in this formula, so then this term is gone. Over here, the R is gone. I just get delta xn is equal to delta n minus 1 times the change in the stock price. And this is exactly what I see here. So they coincide when R is equal to 0. And why did we go through this pain that took us 12 minutes to calculate? Well, it is simply to prove that the discounted wealth process inherits the martingale property. And so now we can prove that. And so to see that x n tilde is a p tilde martingale, we calculate. What do we calculate? We calculate that I'm interested in xn plus 1 tilde, conditional on fn. What will that be? Well, it'll be equal to e tilde of xn plus delta xn tilde. Xn plus 1. Right, xn plus 1 is equal to xn plus delta xn plus 1. And so I have a conditional expectation of a sum. I'll use that. The conditional expectation is linear. The first part is already measurable. xn tilde is measurable at time n. Put them outside. Plus, and then the conditional expectation of the other term. The conditional expectation of the other term is the thing we worked so hard to calculate. It's going to be xn delta xn plus 1. So we need to replace n by n plus 1. So I'm going to get an n here. And then I'm going to get delta is n plus 1 with a tilde on top, given fn. So now we're very similar to the situation we had before. This thing here, this is my holdings at time n. This is fn measurable. So you can go outside. I'm left with the conditional expectation. I'm left with the conditional expectation of delta is n plus 1 given fn. Where this is equal to 0 because is n tilde is a martingale. So that's like the so not only is the discounted stock price a martingale, it's actually true that the discounted wealth process is a martingale as well. So it's easy to get lost in all the calculations here. I wanted to show you all the calculations here so you can see where it's coming from. What this shows is that the discounted wealth process is a martingale. We're not saying anything about the undiscounted wealth process. In general, that's not going to be a martingale. Could we follow this?
Professor, how'd you get the equation right up going from the first equality to the second equality? Yeah, this one.
We just use linearity, right? The expectation of a sum is equal to the expectation of this thing plus the expectation of this thing.
Right, yeah.
The first term here is already measurable. Xn tilde is measurable with respect to Fn. Right? The wealth that you have at time n is known at time n.
So it just comes out and then it becomes 1.
It's not 1.
I mean, it comes out of the, if it's measurable with respect to Fn, it comes out of the expectation. And
Yeah, I mean, if I'm looking at the conditional expectation of a random variable given the random variable, this is the random variable.
okay, yeah.
Yeah.
And
then the second part, this is the change in the discounted wealth at time n plus 1. Maybe it's hard to read this stuff out. This is n plus 1, but because we're looking at it here at n plus 1. So I need a formula for what's that?
so you just substituted it in for
Yeah, I just put it in.
n plus 1
Yeah.
instead of n.
Yeah. And so then you get this. And then in the last step, you now have a product of two things. So when you have a product of two things, you can pull out what's measurable. So that will be delta n, right? Because you know how many stocks you have at time n. So that thing goes outside, and you're left with a conditional expectation of the remaining component. But this thing is 0 because S tilde is a marking. And so then you're left with.
Wait. S tilde is a martingale and it's 0. What? Why does that mean it's 0?
If I'm looking at Sn plus 1 tilde given Fn, this is Sn tilde. Do you agree?
Okay, yes, I agree.
This is the same thing as saying that delta Sn plus 1 tilde 0, right?
Oh, because it doesn't change.
No,
Wait,
if you move this to the other side, then he can go inside the conditional expectation because the discounted stock price is measured.
oh, I see.
Like this here, this is by definition Sn tilde plus 1 minus Sn tilde.
Got it. Okay. Yeah.
Good. Other questions or comments? So what we're going to do next here is we're going to price derivatives. Okay, so as in the one period model, what you're given a payoff. So say a function. You're giving a payoff function. Let's call it Fn. So this is something that goes from say R to R. And so the derivative has a payoff. The derivative's payoff is Fn applied to the stock price, and this is at time capital A. So you're looking at a picture where we're sitting out here at the end. This is where the payoff happens. And then you have a bunch of periods, and you are really interested in what is the price of derivative at time 0. So the question is, how do we move from all the way out here, and then we move backwards? You always, so this should be a mantra you. There are a few things in this class that you should take away. One of the things that you should take away is whenever you have a problem to solve, you start at the end. That means all the way to the right, and then you move forward in time. This is this dynamical programming idea. And I'm sure some of you have seen this in other contexts as well. If you've taken courses in computer science, there will be applications of this idea. If you play some sort of a game and you can have like 5 different options, and you cannot figure out how to play this game optimally. The way you solve such a problem is it is always the same. You start by figuring out what to do when you only have one option, and then when you have only one option, okay, so figure out what it is. Then you go back and say, okay, so how now do we play the game if I had 2 options? And then so forth and so forth. And then you iterate backwards such that you start out with a much simpler problem, and then you move gradually to make it more and more complicated. Right. So the same. This is that principle is called dynamical programming. It's like you want to walk a long distance, right, and you don't know how to do that. Well, you start by walking a smaller distance, and that is what we're doing here. You always start from the right. Like we want the thing all the way on the left, so we're going to take a little step to the right. So we're going to go from time capital N to time capital N minus 1. Like that's the first step. Right. Given we can figure this out, then what we're going to do is we're going to take one more step to the left, and we're going to keep going until we get here to time 0. Okay, dynamical programming. And this is true in all kinds of applications. It's always true when you price derivatives. If whatever problem you're going to be given in this class, and dare I say in all classes of this nature, you should always start with the simplest possible case and then gradually make it more and more complicated. If you start here and try to figure out how to do it, it's hopeless. You have to move in this direction, move from the right to the left. Okay, so how would you do it? Well, how did we do it? How did we do it in the 1 period case? Well, the goal is, so create an initial wealth and create a trading strategy. That's delta 0, delta 1, all the way up to delta n minus 1. But such that what? Such that when you start out with this wealth, this many shares, and then this dynamical way of doing it, the resulting wealth process gives you exactly Fn of Sn. Create these quantities. Before, in the 1 period model, we only had to create these 2. But now in the multi-period model, we have to create more of them. So create them such that this is the case. And our tool is going to be is a martingale structure. And we know what the martingale structure is. Right, so we know based upon the above, we will have that the conditional expectation of x n tilde. So we're going to go one step back. So we're going to go back to f n minus 1. This is going to be exactly x n minus 1 tilde. Okay, so this is the same. This is the same as saying what? That the expectation of x n divided by 1 plus r to the nth given fn minus 1, this is xn minus 1 divided by 1 plus r to the n minus 1. And so I can pull this 1 plus r outside and move over, and I'll end up having that xn divided by 1 plus r given, and this is under the tilde measure, fn minus 1, this is exactly xn minus 1. So this is how I get the wealth at time n minus 1. I have to compute this conditional expectation. And this is good because I'm given exactly what the wealth should be at the end. It should be this fn of Sn minus 1. Right? This here could be, like for a call, this would be fn of Sn would be, what is it? Call is Sn minus k, positive part. For a put, it will be Fn of Sn would be k minus Sn positive pi. So you're given this payoff here at the end of the model. This is where your F lives. This is your Fn. And now what we want to create is this Fn minus 1. We want to go one step back. And so how do we get this Fn minus 1? Well, this here is going to be our Fn minus 1. But this here is going to be our Fn minus 1 of Sn minus 1. And let's try to see if we can figure out what it is. So the left-hand side, I'll write this here as Fn Sn divided by 1 plus r, given Fn minus 1. So the goal is to write my wealth process in terms of the stock at time n minus 1. Okay, so I have to compute this conditional expectation, and I can do that. It's very similar to some of the calculations that we've already done. You will start by replacing Sn by Sn minus 1, so you can start invoking the independence lemma. So you write this here as E tilde Fn, you can put this 1 over 1 plus r outside. You get Fn Sn minus 1, and then you get your sign. And then you condition on Fn minus 1. Right, so we're hunting this function up here, and this is what we have. I can now use the independence lemma. And what can I do? I can write this as 1 over 1 plus r. I'll get a p tilde, and I'll get Fn Sn minus 1, because that's already measurable, and I get the independent, so I take an average. This will be u plus 1 minus p tilde Fn Sn minus 1, and then I'll put in a d. And indeed, you do see that Sn minus 1 is the only random variable that appears on the left-hand side. And so we get, so Fn minus 1 of x should be defined as 1 over 1 plus r p tilde Fn of x u plus 1 minus p tilde Fn of x times d. So that's how we get our wealth at an earlier time. Are there questions on this part? I taught a similar class just a few days ago, and when we got down to here, people were like, this is just confusing. And yeah, I can see the notation is pretty horrendous. And so I figured maybe today we should try, instead of keep doing this stuff, maybe we should just do an example at this point. Even though we're really not completely ready for it, maybe it would be a good idea just to try to do an example to see if this will be easier to comprehend and digest, because this is a bit elaborate. So I looked through the exam questions. I found one that seemed to be okay. It's this question here that I circled, question number 6. So there, what you're given is a very specific function. So you're given say the payoff is it's a quadratic function. So you're given like, what should we say? F n of x, this is given to be x squared. And so what our goal is to find fn minus 1 of x. So this is a function, right? So you should find this function such that if I plug in the stock price at that earlier time, I would get exactly the conditional expectation under this residual measure of Sn squared given Fn. Right, so we're redoing what we just did, but in a more specific example. So how would we go about our day and to do this? Well, we'll use, so again, the key ingredient is the key, which you have to replace Sn by its definition. So this will be Sn, it's defined to be Sn minus 1 times this Bernoulli. And you know that the Bernoulli is the independent. So you plug that in here, and you'll compute the conditional expectation to be, now it's more specific than it was before, it's a square function, so we'll compute this here Sn minus 1, the coin flip time n squared, given Fn minus 1. How would we compute that? Well, you use that the square of a product is, of course, just the product of the squares. And so one part is measurable. You can go outside. And then you're left with the other part. How do we work on the other part? How do we work on this part here? So this one here, use that Sn is Fn measurable.
Do we use that it's independent from the sigma?
Yep. Very good.
Sigma algebra.
Are you starting to see a pattern now in what we're doing?
Kind of.
Yeah.
This is like the thing we did like 2 examples back with the.
We're doing the same thing over and over and over and over and over, right? We're using structure of the binomial model to do these calculations, and there's nothing else. I mean, that's it. That's all we have to do. We just have to get comfortable doing this. So we use the independence. Right, so this here means that this nth coin flip is independent of Fn minus 1, so we are squared. I'm still going to be independent. This is independent of Fn minus 1. And then I'll use that, well, I can work out what this expectation there really is. This is p tilde times u squared plus 1 minus p tilde times d squared. Do not put the square on the p tildes, right? This is not, that's not correct. The square counts on the u and the d. So this gives me the function that I'm looking for. Like I'm looking for this function, so Fn minus 1 of a, this is a squared p tilde u squared plus 1 minus p tilde d squared. I'm choosing an a here because I don't want us to get into a spot where we think that the functions can only be defined if I put an x here or a y here. I can define a is just a dummy. I can, whatever I plug in here, I just have to make sure I plug the same thing in over here. Right, so there's nothing random here on the right hand side. This is just a function like the ones you know from calculus. So that's how we get that function. Right, so my wealth now is, so the wealth, this is the wealth at the last step, is now going to be xn minus 1. This is going to be exactly my fn minus 1 applied to sn minus 1. So that was the first step in this exercise. The second step is, of course, so now we have the wealth. How do we get the portfolio holdings? Maybe before I launch into that, is there another question or comment about what we have on the sheet here?
The question wanted us to find fn minus 1.
Yeah.
Right, and we just said it was equal to x n minus 1.
But this is what we're working with, right? The conditional expectation. The conditional expectation we have here, this is going to be my xn minus 1.
Gotcha. Okay.
This is the one we worked quite hard to get to, right? That was the martingale property. And so we're saying that the wealth at time at an earlier time is given by discounting the wealth at a future time. And so we're starting from the end, so we know exactly what the wealth is going to be at the end. That's just going to be the payoff of the derivative. So now what is the wealth then one point in time earlier is going to be this conditional expectation, and we're trying to figure out what that conditional expectation is. It's some function of the stock price at that time. And in this particular example, it's this function here.
Okay, so that's the thing after the so is the answer.
Yep, that's it. Right? The question is find a function such that this holds. So this is the function. We work here on we want a function such that this is true. So we go through all this and we figure out, okay, so this is my function. Now again,
okay.
then I know that the wealth is going to be exactly, like the wealth is random, the function is not random, the wealth is random, and I get the random wealth by plugging in the stock price into this function.
Got it. Okay, yeah, that makes sense.
So then the next part to the question is you find delta. What you want to find, this is what we want to do, right? You want to find how much we're going to invest such that at the end, I get exactly this Sn squared. And this problem here has an interest rate of 0. I should have said that somewhere. So we don't have to put tildes anywhere. So we're just working with an interest rate of 0 for simplicity, so we don't have to discount. So find delta n minus 1 such that this is true where the wealth at the previous time, this is exactly that thing we had up on the previous slide. This was fn minus 1 is n minus 1. So how do we do that? Well, remember, what I have here is we can use the connection. We can use that delta x n is equal to xn minus 1. And I can also use that we had a formula for this. This was my delta. This was my delta n minus 1 times Sn minus Sn minus 1. All right, this was the self-financing condition. We had it in the discounted market. We had that in the discounted market over on this slide here. Like the change in the discounted wealth was exactly the position times the price change. But because in this particular problem, the problem assumes this R being 0, so there's no difference between discounted wealth and undiscounted wealth, and so I just get this property. Right, so I can work out then on the left hand side I want to have this Sn squared, and instead of xn, what I'll have is I'll have xn minus 1 plus delta n minus 1, and then the price change. So I'll have that. We also had discussions about this is really not just one equation, this is really two equations. This here is the same as, like, the randomness that I'm dealing with is this Sn. And I can write Sn.
Okay, come on. Bye. Bye.
So I can write Sn here. I can write Sn here as Sn minus 1 times my psi. So psi can be either u or d. So I'll get a pair of equations here. I'll get a d squared. Like this equation up here, there are two possibilities for Sn. If you know what Sn minus 1 is, it can either be Sn minus 1 times u or Sn minus 1 times d. And then on the right hand side, what will I get? I'll have delta n minus 1, and then the same thing. I'll have here, this will be Sn minus 1 times u minus Sn minus 1. And then down here, I'll get something similar, but instead of u, I'll get d. I'll get these two equations. So you solve. Solve for xn minus 1, and you solve for delta n minus 1. This should be quite familiar to you from the one period model. Now we're sitting out here at the end, sitting out here at the end of the picture, and we're just going one period to the left. Sitting out here, we have two equations and two unknowns. We solve them. Given my ability to do this, let me write down what my solution is. This is delta n minus 1 is what? I get that this is S n minus 1 times u plus d. And I get that xn minus 1 is equal to what do I get? I get that this is equal to S n minus 1 squared u squared minus, I'll just pick one of these. Pick this one. Delta n minus 1 is n minus 1, you have u minus 1. there is a potential problem here. So I solve my two equations and two unknowns. I solve them, I get this. So we need to make a sanity check. We have those a lot in this class. You need to make a sanity check, right? I want to make sure that this solution, xn minus 1, actually this guy here, we want to make sure that xn, which is this mess here, I want to make sure that this is actually equal to, this fn minus 1 of Sn minus 1. I mean, otherwise it won't work, right? So we need to have a sanity check. But it's not so bad because we have a formula for it. This is my formula. So we can write out what this is. It's the same. This is the same as saying Sn minus 1 squared u squared minus delta n minus 1 Sn minus 1 u minus 1. That this is the same thing as this fn minus 1 Sn minus 1, and I have a formula for that, so I'm just plug in the formula. There's a typo here, right? Here there's n minus 1, it got this, there's a minus 1 missing and a minus 1 missing here. Formula comes over here as Sn minus 1 squared p tilde u squared plus 1 minus p tilde d squared. So we have to just make sure we didn't make a mistake. Check this equation that this is true. Okay, so I'll leave that to you guys to play with, but when there is a chance to make sure that you didn't make a mistake, you try to do it. But what this calculation shows you is if I can find these functions, if I can find these conditional expectation functions, well then by moving backward, I can also create these deltas. I think questions on this example we did here. This is an old exam question that was handed out a few years ago.
I have a question. I got completely lost towards the end when you started writing a system of equations. Like,
do you recognize this? Do you recognize this structure here from the one-period model?
It's a little. I'm not really. What's it supposed to resemble?
Like the replicating equations we had in.
Oh, okay. Okay, I gotcha.
Right. In the very beginning, we were hunting either delta 0 and delta, or we were hunting x0 and delta, such that the wealth did something at some point. Right. So now we want our wealth. We want our wealth at the end to give me that, because it's what I'm thinking about as my derivative.
Okay.
So what is the wealth at an earlier time if I want this condition here to hold? Well, the claim is that it is exactly this fn minus 1 applied to Sn minus 1. Okay, so for that to make sense, I need to be able to say that if I start out with this amount of dollars at time n minus 1, I can find a way to invest in the stock such that at the time point later, I get exactly Sn squared.
Okay.
That makes sense, right?
Yeah. This
amount of money at time n minus 1, tell me how to invest in the stock such that one period later, I'll get exactly that payoff. If I can do that, then the price of this payoff here at time n minus 1 should be exactly the number of dollars I need to start out with. No?
Okay, no, you just froze. Sorry.
Okay, so if I tell you that I need $5 today, then I can trade such that at the end, I get what I have here on the right-hand side, the stock price squared. Well, what would be the price of this stock price squared? Not at time n, but at time n minus 1. Well, it'll be those $5. Because if they differ, there'll be arbitrage.
Say it again about the $5.
So imagine that the price of this derivative here
Mm-hmm.
at time n minus 1 would not be what I have here. Imagine it would be a higher number or a smaller number. Then what would you do?
Okay, that's what you're saying with the arbitrage. Okay.
We had that argument in the beginning of the class.
Yeah.
Okay, so then construct this delta that will take you from this initial wealth to this terminal wealth. Then you have to write out. You have to write out what does it mean for xn to be equal to Sn squared. Well, this is an equality between random variables. So that's what I've written out here, right? Xn is exactly xn minus 1 plus this delta plus the price change. No?
Yeah. No, that's yes.
Agree on
Yes.
that? Okay, so then what is, if you're sitting at time n minus 1, what is random in this equation? It's not random how much wealth you have at the beginning. It's not random how many shares you have. The only random
Stock price.
is the stock price, right? And how many possible values are there? Well, if you're sitting at time n minus 1, there are only 2 possible values. It's either going to go up or it's going to go down. So this equation here is really these 2 equations here. Because Sn is equal to Sn minus 1 times u in the upstate, and is equal to S. Right?
Oh, I understand. That's how you get your system of equations to solve for Sn minus 1. Yeah. Yeah, no, I understand where they come from now.
Yeah, so this Sn, you have it here and you have it here. So you need to do it on both of them. Right? You cannot just put in Sn minus 1 on the left-hand side. You also need to substitute out what Sn is on the right-hand side. So you get these 2 equations, and the 2 unknowns will be the wealth and the portfolio, how many stocks you hold. So you have 2 equations and 2 unknowns, you solve them.
Got it. I understand now.
So now we get 2 solutions. So you're happy with this one because this was exactly what you needed, but you need to be consistent, right? Because we have claimed that this xn, you can see you get this this particular, if I know what delta is, I just pick one of these 2 equations, and that will give me what xn minus 1 is. So I need to have consistency because this xn minus 1, we had it already on one of the previous slides, so there was no way around it, right? That xn minus 1 had to be this function here. So I should have a sanity check, namely that this is also going to be the case in my example. So I have my xn minus 1, I have my function, they better coincide. Because if they don't coincide, there's a problem. So this is just a way to check your analysis that this actually holds. And it's not hard. You just take the solution you got out from the linear equation sets and take the function that you calculated in the previous question and just see that they match up. Right? I have an expression here for this part here, right? I can substitute that in there. Fn minus 1, I can pick the function from the first part. And so this one here, I'll use the first part. And so they have to line up. And they do. Right, so I just plug in the 2 expressions and you just plug in what your position is. That was the first part here. Plug that in there. You're going to get something with Sn minus 1. In this term, so you're going to get a squared here that goes off with this square. So you're going to have a u squared. You're going to have something else over here, and then check that when you plug in what p tilde is, that everything lines up. It does. It has to.
So we're checking if the payoff at n-1 is equal to the wealth because x n-1 is the wealth, right?
That's right. But we don't. I don't like saying the payoff at time n-1 because the payoff is something that comes only at the end. It only comes at time n.
So how do we refer to it?
Like what's on the right hand side here is this conditional expectation.
Right.
What we're saying is this conditional expectation has to line up with the wealth.
Okay. Okay. Thank you.
Just ask yourself, what do you think happens if they don't line up?
Then there'll be arbitrage, right?
There will be arbitrage. Like if the derivative trades at a price at time n-1 that is different than this conditional expectation, then what this means is that you can set up a replicating portfolio that trades at a different price at time n-1. But you know at time n, they have the same values. This is inconsistent with arbitrage, right? Because you're going to, at time n-1, you're going to sell the expensive one and buy the cheap one. That's going to give you money now, and you know, and at the end of the next period, the two things will net out to a zero. Yeah, so I don't like the reason that I'm saying this thing about the derivative, the payoff at time n-1. It is not just to be a stickler. It is, even though we won't have time to do it in here, the next thing that's coming in the textbook, namely down here in the last at the bottom of the page, it's this American derivatives. And American derivatives are a little bit different. They have their payoffs are not bound to happen at the end. There can be payoffs coming out at different times. So just to make sure we don't get that into our material just yet, I like to think about the payoffs always for European derivatives. They happen at the end.
Right. Right. That makes sense.
Okay, I think this is actually a pretty good place to call it quits. So just once again, most of you have signed up for a slot for the oral exams, and that's great. Check out that announcement that lists all the students' names and make sure I put you into the right bin. If you haven't signed up, send me an email, please, so we can get you put into one of those bins. Otherwise, there are office hours tomorrow. I should also say that some of you have asked for more options for office hours, so I sent out an email about now there are 3 different slots for office hours for 485. Some of them are shared with another class, so currently it's not a big deal because the other class, we're covering more or less the same material. That's going to end soon, but the other class, they also don't seem to use my office hours very much, so it's not like there's a lot of traffic there. So I'm hoping this can alleviate some of the pressure on the students that have classes at the same time as my office hours. Okay, that's all for me. If there are more questions, we can do that. Otherwise, I bid you a good night.
Good night. Thanks, Professor.
You're welcome.